Hi everyone, welcome to my YouTube channel. So today we will be discussing a question that has been taken from the topic elastic collision. Very recently I came across this question and I thought that the solution might be helpful for a lot of students who are aspiring physics. So the question says that ASU scientists used the Rutherford Backscattering Facility to determine the atomic composition of materials. In this facility, helium atom ions are accelerated to high kinetic energy and strike a target. A fraction of the helium atom bounce back, reversing their direction of motion by 180 degrees. That means after collision, the angle between the projectile ion and the target atom is 180 degrees. This occurs when the helium ion hits the nucleus of a target atom head on. A nearby detector measures the kinetic energy of the bouncing helium ion, and from this energy, one can deduce the mass of the atom that was hit. Suppose that the material contains silicon, that means the target crystal lattice that we are considering is consisting of silicon and germanium. Silicon is having 28 atomic mass unit and germanium is having 73 atomic mass unit. So in this question we have to figure out the ratio of the kinetic energies of the helium ion bouncing off silicon atoms and the helium ion bouncing off the germanium atoms. And we also have to assume that the collision is elastic. Elastic as in the kinetic energy as well as the momentum remains conserved in the system. So, a most important data provided in this question is that the scientists are using the Rutherford Backscattering Facility. So, in the Rutherford Backscattering spectrometry, we came across a very important term which we refer as kinematic factor. Now, what is this? Elastic energy transfer from a projectile to a target atom can be calculated from collision kinematics. So, kinematic factor is basically the ratio of the energy of the target atom and that of the projectile, which is given by the formula m2 square minus m1 square sine square theta plus m1 cos theta over m1 plus m2 square. So basically now kinematic factor here is just giving you the ratio between the silicon and the helium atom. Still we are not considering the germanium, that would be calculated separately. Okay, so three things which are important over here is m1, m2 and theta. So what is m1 in this case? It's the mass of the helium atom, which is 4 atomic mass unit, and that of m2 is 28 atomic mass unit, and theta given 180 degrees. So calculating the ratio, it is equal to root under 28 square minus m1 square is 4 square times sine square 180 degrees plus 4 times cos of 180 degrees over 28 plus 4 whole square. So that is equal to, now we know that sine 80 degree 180 degree is equals to 0. So that becomes 28 square minus 0 plus 4 times, and cos 180 degree is negative 1 over 32. So that becomes 28 minus 4 over 32 whole square. That's 24 square over 32 square. So we will leave our calculation till here only, because ultimately it's all about the ratio. Now we will figure out the kinematic factor, that is the energy possessed by the germanium atom and that of the helium ion. Again using the same formula, but this time the m2 over here is that of the germanium, so we would be using 77 square, rest would be the same, and then 4 times negative 1 over 77 plus 4 whole square that comes out to be around 77 minus 4 over 81 square. So that's 73 square over 81 square. So what we are concerned with is figuring out the ratio of the kinetic energy of the helium ion bouncing of silicon atom to the helium ion bouncing of the germanium atom. So that is equal to, if I represent this as K1 and this one as K2, so K1 over K2 is equal to 24 square over 32 square times 73 square times 81 square, which comes out to be around 0.69, which is 0.7. So I can say silicon over germanium is equal to 0.7. So that means our third option is absolutely correct. So I guess this solution would be helpful enough for all the students, and I hope that you like the way I taught you this solution. So make sure you like the video and subscribe to my channel. Thank you.